Today we're going to talk about what it means for a function to be differentiable. And in its most basic idea, you can initially think about differentiability as just being the domain of the derivative. So a function is going to be differentiable at x equals c if f prime of c, if the derivative exists at x equals c. So it's a pretty simple idea, basically saying that x equals c is in the domain of f prime. So when you think about if you're actually given what the function is, the algebraic definition of the function, in theory you could find the derivative and just look at the domain of the derivative. However, what we want to focus on here in this video is how can I tell by looking at a graph of the function of f of x where a function might be differentiable, meaning where does the derivative exist. So in words, kind of a mental vocabulary that you could say to yourself might be this. In order for the derivative to exist, because the derivative is a limit definition, what we need is we're going to need, so what we need here, let's put this in gray, is we need the derivative, or let's say like the slope of the tangent line, we need the derivative from the left to equal the derivative, or the slope of the tangent line, from the right. So the derivative, we've spent a couple of sections talking about the limit definition of the derivative. So we need the slope of the tangent line from the left to equal the derivative, or the slope of the tangent line from the right. So that's kind of maybe a nice way to have that phrased in your head. A little more formally, let's write this out with our limit definition actually from 2.1. So what we want is we need the limit as x approaches c from the left of f of x minus f of c over x minus c to equal the limit as x approaches c from the right, again, f of x minus f of c. So this is our limit definition of the derivative from the first section. And the reason I'm going back to that one here is we're really focusing on differentiability at a specified point. Does the derivative exist at that point? And so that's kind of why I'm going back to our first definition here. So if you were to take a look at this graph and you were to kind of think about, on each of these, you're somewhat ignoring the other side temporarily. So when you're looking at the derivative from the left, kind of forget about everything. And if I was in person here, I'd be putting my hand over this whole right-hand side. So forget about the right-hand side. Just focus on what's happening on the left-hand side. And as you think about the slope of the tangent line at x equals c coming from the left, that's going to be this blue tangent line you have drawn. Okay, well then if I was to look at the slope of the tangent line from the right at that point, so again, kind of forget about all this for right now, just focus on coming from the right. And if you were to look at the slope of the tangent line coming from the right at x equals c, that would be shown by that line in red. And clearly, these two slopes are not equal to each other. So let's even write out here, this is the slope of the tangent line from the left, and so that's this written out real properly, limit as x approaches c from the left, f of x minus f of c over x minus c. And then what we have on the red line here, this represents your slope of the tangent line coming from the right, and the slope of the tangent line from the right, written more formally, limit as x approaches c from the right, f of x minus f of c over x minus c. Okay, now obviously these two are not equal to each other. So very clearly we can see that these two are not equal to one another. So it's pretty clear that the derivative from the left and the derivative from the right here are not equal to each other. And so what that would mean is we would say that f is not differentiable at x equals c. Okay, so this is kind of the big idea here. All right, so before we go on, we're going to look at some more examples of where functions are not differentiable. And before we do that, though, we're going to make a quick connection here between differentiability and continuity. So again, think about for a function to be differentiable, the derivative has to exist at that point. So first of all, the point is defined on the derivative. And then also when you go back to thinking about the graph of the function, you're thinking about, just a quick sketch, I'll erase it, but you're thinking about, a situation where slopes of the tangent lines from one side are approaching slopes of the tangent lines from the other side. And, we're going into this point where that point exists. There is a unique tangent line there. That tangent line exists, and the slopes of the tangent lines from the left are approaching the slopes of the tangent lines from the right, and that unique tangent line exists at that point. It's defined there. So kind of all that together, we're really saying that if you're differentiable, you're definitely going to have to be continuous. So if a function is differentiable at x equals c, then it is going to be continuous at x equals c. So what we have here is this notion that we want to think of, which is that differentiability is going to imply continuity. Now, the contrapositive of that, if you take a logic class, you would learn about things like this, would mean that if a function is, if we are not differentiable, erase, erase, erase. I started to write out the wrong side of that. The thing you have to be careful of. So in this situation, if we are not continuous at x equals c, then we are not differentiable at x equals c. Okay, so in order to be differentiable, there has to be a unique tangent line that exists, a point defined on the function, where then that tangent line has that unique tangent line at that point. So it's also okay to say that if you are not continuous, then you are not differentiable. So that is a valid conclusion as well. So it's okay to say if you're not continuous, then that also implies that you are not differentiable. Okay, so those two are both okay to say. The thing you have to be careful of here is that you can't say that because you are, this is your caution here, if you are continuous at x equals c, this does not imply that you are differentiable. And sometimes after that first statement that we have up above, sometimes people make that mistake. So we want to be really careful on something like this, that this is not, so notice the big old not here. It is not okay to say, continuity does not imply differentiability. Okay, so be careful on that. All right, so what I really want to get to is these examples here on the bottom. I want to get to these different examples where a function is not continuous. So let's start with the example that we kind of left off with up here on the top, which basically was observing that if a function is not continuous, then it's not differentiable. So that's the one right in the middle right here. So if we are discontinuous at x equals a, then this is going to immediately imply that we are not differentiable. Okay, so that's, I'm just going to say not diff at x equals a. Okay, so that's sort of our first one that we want to be aware of. Okay, now let's get into some of the other ones. And I added a couple on the ends here as well. So the very first one, if we go from left to right, the endpoint issue, the only time we've really seen that is we did a problem by hand where we found f, and then earlier in the section we found f prime. It involved a radical, and we compared their domains. And we saw that the domain of f included the endpoint, but the domain of f prime did not. And so what's kind of the reasoning here? Why are we not differentiable kind of at an endpoint like this? And the reason is because we need these left and right limits to equal each other, the derivative from the left and the derivative from the right. So in situations like this, what's going to be happening is the limit as x approaches a from one of the sides, in this case it's from the left, of the derivative is simply not going to exist. There is no derivative from the left if we have an endpoint here. There's no function to the left, so there's not going to be a slope of a tangent line coming from the left. There's nothing there. So in situations like this, the endpoint then is not going to be a place where the function is going to be differentiable. So it could either be, and I'll put this kind of in parentheses down below, it could also be this one in this picture, it's the left endpoint, but you also could have the situation where if the endpoint was on the right end of the function, then maybe it's the limit as x approaches a from the right of f prime that doesn't exist. So notice down below here, I'm taking the liberty of a little shorthand. I'm no longer writing out the limit as x approaches a from the left or right of f of x minus f of a over x minus a. I'm just denoting that of f prime. So we're still talking about the same ideas here, which is this idea that the slope of the tangent line from the left has to equal the slope of the tangent line from the right. And so in our first example, if you don't have a slope of a tangent line coming from, say, one side or the other, then it can't be differentiable. They can't be equal if one side simply does not exist. Okay, second one. Maybe scribble out where in front of this it did say cusp/corner. I'm going to break off the cusp as a different case here. So a corner point. This is like our opening example. I took the liberty of kind of writing in potentially what the slope from the left is a line, so maybe that slope is 1. And maybe the slope from the right is like approximately -4. I just sort of approximated there. So this is the opening example, so I'm not going to take a ton of time on this one. We've seen this already. So the issue here is because these limits both exist. The limit, the slope of the tangent line from the left exists, and so does the slope of the tangent line from the right. It exists, but the problem is that these two slopes are not coming into the same value. The slope of the tangent line from the left is not equal to the slope of the tangent line from the right. All right, we've already broke down. If it's discontinuous, you're definitely not differentiable. Let's take a look at the vertical tangency issues in the last two cases. So what we have going on here, and I've kind of drawn in some slopes of tangent lines, and this is often helpful too as you're kind of visualizing what's happening here. So if you look at this coming in from the left on this case, so if you notice, I'm going to draw over these lines again here, but if you look at the slopes, these are definitely, in this case, negative slopes. And what's happening as I'm coming from the left is these are getting more and more steep, and they're approaching very, very large negative numbers. So maybe I'm going -0.5, -1, -2, -5, -100. And then it's doing the same basic thing from the right. These are negative slopes, so maybe it's -1, -2, -3, -10, -100. These slopes coming from both sides are getting very, very large, and in this example, They're both getting very large, but they're negative numbers. You can also see it just because the overall decrease of the function in this area, it has a negative rate of change. So what's happening here? And I'll start by saying a lot of folks, when they first learn this, and it's totally fine, you can initially just first on a basic level, you can think to yourself, well, the reason is because a vertical line has an undefined slope. I know that from basic algebra. So if a vertical line's slope is undefined, the slope is the derivative. So it's undefined. It doesn't exist. That's a fine way to think about it. We're just getting more specific. So what are we seeing here? We are seeing that the limit as x approaches a from the left of f prime, so the slope of the tangent line from the left, and we're seeing that the limit as x approaches a from the right, the slope of the tangent line from the right on the derivative, these are both going to negative infinity, and that doesn't exist. That's not a real number. That's undefined. As a slope, we'd say it's undefined in basic algebra days. And so for this limit, it's going to negative infinity. It doesn't exist. So f prime would not be defined at x equals a. Now, in other graphs, let me just mention, it could be that you have a situation where maybe potentially the function was increasing instead. And pardon the graph not being so perfect here. That's an awfully sharp turn there. Actually, let me draw that again. So you could have something that's maybe more there. That's a little bit better. Increasing. And the vertical tangency I'm going to draw in right here. It could be that both of those are going to positive infinity. So it could be that these limits are both going to positive infinity. So it could be that the limit as x approaches a from the left of f prime and the limit as x approaches a from the right of f prime, they could both be going to positive infinity as well if the function had been increasing in shape instead. Okay, but they are both either going to infinity or they are both going to negative infinity. All right, our last example, this cusp point. So this cusp point is also a vertical tangency, but obviously it looks very different here. So we broke it off in its own case. And so, again, I've kind of lightly drawn in some little tangent lines kind of approaching from, if you notice those tangent lines coming from the left, they're all negative, getting very, very steep. So going to really large negative numbers. So maybe it's, -1, -2, -100, and so on. So if I was to write this out, I would observe in this situation that the limit as x approaches a from the left on this example of f prime is going to negative infinity. But if I look at the slope of the tangent line approaching a from the right, those values are positive slopes, getting very, very steep, getting very large, but they are going to positive infinity. So with a cusp point, and I'll just again make the comment here, I'll just say, or the plus and minus infinities could be switched. Okay, but one is, the first one could have been positive infinity, the second one could have been negative infinity. If you had a graph that maybe looked something like this. Okay, so in that situation, the one from the left would have been going to positive infinity and the one from the right would have been going to negative infinity. All right, but in either case, they are both going, the two one-sided limits here are going to different infinities, let's say. So the reason I'm making kind of a big deal about some of these observations here is because these are going to have different implications when we get back in the next video to connecting the graph of a function and the graph of its derivative function. So these are going to visually kind of manifest themselves differently in the graphs of f prime. And so that's why we're breaking apart all these cases in terms of what, by definition, kind of what is happening here. So that's what we're going to come back and look at next time, is then let's go back, look at connecting graphs of functions with their derivatives, and in particular, like what will a corner point look like on the graph of the derivative function? What will happen to these vertical tangencies when we actually graph the derivative functions? Okay, so that's what we're going to look at next time.